So this is a very informal session because most of you are running some biometric experiments, and you may have not got used to Matlab. And I've actually written a tutorial to do that. Okay, and so today I'm going to show you how to use Git to check out the repository. If you haven't used Git before, this would be a good opportunity for you to see how it works. And then I'll show you how to run experiments in Matlab. And finally, if there is a bit of time, I can give some advice on writing reports. Okay, so that is quite general, something that hopefully is useful for you. And if you are not doing biometric experiments, that's still fine. You'll be exposed to how you use Matlab for data analysis. Okay, although I'm not actually showing how you actually do data analysis using Matlab, I'm just showing you how to run biometric experiments. But you have the first test of how Matlab is like. So in any case, it will be useful for you. Okay. The first thing I do is to check out. Okay, so I'm gonna launch here. This is a Cygwin. My setup is of Microsoft Windows, but I use Cygwin because it's got command line, and it's got Git installed. Okay, so the Git is there. So it's a software, version control software. It's useful because you want to make sure that your source code is not lost if your computer is dead, your hard disk is dead. You can still have your data saved somewhere and back up somewhere. Okay. So first thing I like to do is go and check out the tutorial. So biometric experiment design tutorial. So that is the one. This is a publicly available Git. So all you need to do is to check things out. And I'm going to navigate to my folder, which is here, and I'm going to create one called Biometrics. Okay. Now I'm going to navigate to the folder in Cygwin. So you change directory, paste the path in Windows, and now I'm in the Cygwin directory. Right? So everything's empty there. I can go back and check the directory by running the Explorer command, and I get the Windows I want. Okay, so it's the same thing here. I'm going to check the source code out from there, essentially downloading the source code from there, because it's been configured to be publicly accessible. So I'm going to do this, git clone. So it's downloading the data and everything. Now this particular experiment runs, so you can see the folder, and there are some features coming out of this. Yeah. So this is a fingerprint experiment. See lots of fingers. Yeah. And we have a software that produces a score. So given two fingerprint images, how similar they are. Okay. Now, obviously you guys are not running the fingerprint experiment, so I don't need to show you that. But I need to show you how the experiment is designed. That's the purpose of the experiment. So if you're going to collect some data, you're going to say this is from user 1, and that's his first impression. So finger 1, impression 1. Okay, and then user finger 1, impression 2. And so there are actually 15 images there. See 15 of them? 5, a batch of 5, another 5, another 5. So there are 3 fingers, each time 5 impressions. That makes 15 fingers, right? So if you collect experiments, signature, keystroke, or whatever that you're going to decide to use, you're going to collect
Actually, it was in 41.
Oh, sorry. Yeah. So you have So you're going to run experiments that compare these 15 images from 3 fingers, yeah? And if you are good enough, you can verify these are from the same fingers. Can you? A trained expert will be able to do so. It's quite difficult because of the impression and they are all different, yeah? So I have written some scripts here. The script here is called Matlab extra, not this one, sorry. I think it's called process here. So I got Notepad++ installed that shows you how the experiment was run. Okay, so it's all in bash script. So when I do the git command, I'm actually in bash. Okay, so but what I'm trying to say, I'm going to skip the details, but maybe just a quick explanation of what happened to the script. So it's going to convert the image from PNG file to WSQ. Okay, so you may want to do some conversion, one image at a time. So maybe there's nothing to be done for keystrokes, but for fingerprint, you need to convert the PNG file to WSQ file. Okay, but this is because the software is taking only WSQ file. Okay, and then from there we're going to convert so we do a loop and then each time convert the file. In fact, I think I should be able to run this here. See if I got a command. So I got a command, so I can actually run the program just like that. Okay, but not all the commands can be run because I may not have all the stuff there. Oh, I'm in the wrong directory. So yeah, so these are the images, yeah. So WSQ file has been generated, but I can run the commands and then it will actually convert the files from PNG to WSQ. So there'll be, for each PNG file, there is a WSQ file. Okay. So this file has been updated, so Git will actually found out that the Git status will tell you that this file has been modified. Okay. Now, for those who haven't used Git, so when you change some files, it get modified. You're gonna Git commit the changes locally. Okay, so I commit and say modify the WSQ files. Okay, I pretend Git commit. Okay, so I commit the changes. Oh, I need to put in fact, sorry, it's actually git add. This is a shortcut actually. I need to put an add there. So normally you git add the file. So the normal procedure is to git add all the WSQ file, and if you do the git status again, you see they all turn green. Yeah. So they have been added to be ready for the next commit. So when I put a commit, all the files that are modified will be pushed to the repository. Okay, they've been staged for to be committed. Okay, so if I done the work already, pretend that I've finished my work, I do git commit and say modify WSQ files. Okay, so I commit it, and then now I need to push it back to the server. Yeah, because now it's actually committed locally, but it hasn't been uploaded to the internet, to the cloud. So I can git push, and then the whole thing will get pushed up. Okay. At the moment, this command does nothing because it was just changing the files. It was exactly the same thing. Yeah, the WSQ files were already there. But I just show you that is a normal way of you do the session. So if I quickly look at the history, you do your job. You clone it. The first thing you do is git pull to get your the first thing you start when you start working afresh is to pull any changes that have been made, especially if you work with other team members. Pull the updates down, and then you make changes. After that, you add the changes, git add, and then you can always check the status of the file using git status, and then finally you git commit. After you commit, you git push. That's the order of how you do the source code control. Is that alright? That's for Git, yeah? So I'm gonna, if you have no questions, I'm gonna park the Git command aside and now deal with the biometric experiment stuff. Yes.
You're using Google Drive, the shared folder we have.
Oh, yeah. So that's another option. So if you Google Drive, that's fine. Yeah, you can use Google Drive, but my Google Drive is a bit limited in size, so yeah. But in programming, we mainly use this. If as team working now, okay, Google Drive is a different thing. You can also collaborate in Google Drive. Okay, but that is a different technology. Okay, right. Shall we come back to the biometric experiments? It was a bit of deviation, but now focus on this one. So once you're done this one, so the next bit of command cannot be run because this is fingerprint specific stuff. Okay, so basically you take an image from there. I is an image, the WSQ image, and then convert it to some features. So features would be files that you can see in the feature directory. For each file 1-1, you know, there's file name still there, but then you produce some features. Okay, so the features is XYT, for example. So that's a file name, and you can actually print out to see the minutia. So it's just a file with some minutia, X and Y location, and then orientation, and then the quality. The last column is orientation. You don't need to know anything about this because none of you are doing fingerprint recognition, but the principle is still the same. You take an input file and produce some features as output. Okay, so there's always a file you take as input and then produce something as output, and you need to write that program. It's called feature extraction. Okay, so one input raw data and output some features. Okay, so I'm teaching you the principle here. So you got some features coming up, and then the next bit of the program, which we're not going to run again because none of us are doing fingerprint recognition. But the idea is there is a command line we call bozo3, and then take the file names. So I can run bits of the program, but not all of that. But so what it does is the matching goes like this. Yeah. So come look at me rather than look at the screen. Yeah? You have a list of files, 15 of them. You're going to take one of the 15 file compared to each of the list of the 15 files. So you get 15 scores, right? Basically, take one file and compare all of them that in the gallery. You get there are 15 query samples, so you get 15 scores, right? But that was the first file that you taken. You take the second file, compared with the 15 files there, and then you get another 15 scores. So essentially, if you have 15 files, you do a exhaustive comparison, you get a matrix of 15 by 15, right? Make sense? Yeah? So if you have 100 samples, you're going to do an exhaustive pairwise comparisons, you'll get 100 by 100 samples. Is that correct? Okay? So what this program does is first construct the file and create a list XYT and a list. So that create a list of files. So you can actually check that. It's actually contain the name of these 15 files. Okay, a list of 15 files. And the next bit of the program says that I'm going to compare, take one file of each, and then compare with the list. Compare the list, yeah? The gallery is a list. Match this file with the list, and then print the output somewhere. Okay, print it to output it to another file. Okay, so it's called fname score. So in the output of the program, you can see there are 15 files. Each of them just contains some scores. Yeah, so if you look at 1.1, you get 15 scores. Okay, now this score is very high because it's a similarity score. The file was comparing to itself, so you get very high scores. Okay, if you check the second one, then the second score is extremely high, and you're comparing the same file, so this score is not useful. Okay, so I got 15 files with the 15 scores. Now I'm going to use Matlab to process. This is where the Matlab comes in. Okay, so I'm going to park this aside and now go to Matlab and load those scores. Okay. Okay, so and I've got a Matlab script already ready in the directory main underscore process. Yeah, so I'm gonna go ahead and load that in Matlab. Okay, so that's file path, and I got Matlab 2016B installed. This is the latest version. So now we go to Matlab. Okay, another piece of tools. So for Sanket, where it's absent, I've done git command lines. I've done example of running experiments using bash script in command line, normally done in Linux. Now I'm loading the scores in Matlab. I'm recording all this so you can see, look at the video later on. Okay. Alright, now we go and load the files. Now, of course, if you're using Android or using Java, you run your program, you must use some command line to generate some score somehow, right? So I assume that you have generated your own, built your own classifiers, or you use an SDK that can produce, that can compare to, that can do the feature extraction, and then you have you also develop another function that is to compare to given two features, produce an output. That's a classifier, or build a classifier for each user, and then take a list of query samples, say 50 of them, then you produce 50 scores. Okay. Now, if you build a classifier, you will ask how many users do I, how many registered enrollment users do I have? If I have 100 enrollment users, I'm going to develop 100 classifiers, right? 100 binary classifier, one specific to each user. So I have the enrollment ready. I built 100 classifiers. Now I look at the query samples, which is another set of samples, and then pass, maybe I've say 50 samples. I'm going to pass these 50 samples to each of these 100 classifiers. Okay, so I'll get the scores in the end of 50 by 100. Make sense? Okay, so that's how you do a matching experiments. Now in our experiments, I've just used 15 scores. So I'm going to do 15 by 15. I should get a square matrix of 15 by 15. Okay, so this script will load the file. Okay, first it's going to load the file names. I don't know if it's going to run like this. Yep, okay. So the file name has been loaded. Okay, it's good. File name is there. So this Matlab, have you seen this Matlab environment before? Is it the first time for all of you? Yeah? You done this? Alright, okay. So here is your directory. And the middle bit is your program, where you write a program. But I can undock it. So depending on what you like, I normally undock this stuff so it's coming out. So I got a full command screen here. And then the right hand side is your workspace, where any memory that is loaded, any variables in memory, you can always check the value of this stuff. You can see there, the file is there. So this is a Matlab environment. So very useful for quick prototyping. And this is essentially what you're doing in biometrics experiments. Okay. Next step is we're going to load the scores into a big matrix. So you don't even have to declare the variable. You do a for loop of the number of file names. So this gives you 15 file names, number of elements. Okay. So, and I like to run that section of the code. I just press Control Enter. So what it does is actually loading the scores. And then underneath, I've got command that show the image in a 15 by 15 square matrix. So you get this image. Okay. So the rows 15, column 15. So good, 15 by 15 matrix. And this is what I loaded. very quickly. Okay, and the color means something here. The color is how similar they are, because in the diagonals these are exactly the same samples, and we're doing cross exhaustive pairwise comparison, so we get something like this. And we also expect the scores to be symmetrical. You can see that they are, it's symmetric. The diagonal above and below look similar, but actually they don't contain the same value. They are not exactly the same value. Why? Any idea? You see, that's 33, that's 44, whereas you would expect it to be exactly the same. So in fingerprint experiment comparison, if I compare template A with template B, it is not the same as comparing template B to template A, because the comparison is not symmetric. Okay, it's not symmetrical. It's not the same thing. But if you do cross correlation, comparing two face features, two feature vectors, and you use a distance metric, then you would have exactly the same scores. But because fingerprint experiments, the distance function is a bit slightly complicated, so it's not the same. Okay, so what I normally do is to okay, now park that aside. I can get the symmetrical score below. So the way I do it is to take the upper triangular matrix and the lower triangular matrix, and then take the average of the two. Right. Okay. So let's look at what we're going to do. Oh, in fact, I can't remember what I do exactly here, but I'll follow the program. Yeah. Set the diagonal score to 0. So because the diagonal is not important, it's meaningless. It's just comparing the same thing. So I'm going to create a mask. Okay. The mask is this function. Okay. So if I of 2 will give you a matrix of this like this. A 2 by 2 matrix, or I of a 3 will give you something like this. Okay, so it's just an identity matrix. So I'm creating an identity matrix of 15 elements and call it a mask. Okay, so I'm going to multiply the mask into the square matrix of score. So you can see the mask looks like that. Yeah, and it's 1 minus, so then the diagonal is exactly 0. So I'm going to multiply the mask into the score. So what happens when I do that? I'm going to multiply this mask into the score matrix that you have seen here. What happened?
Element-wise multiplying.
Yeah, it's element-wise multiplying.
Diagonals become 0.
Exactly. Yeah. So now I display the element now becomes 0, and suddenly I can see something in the matrix, whereas before I couldn't, because the diagonal matrix was dominated by the very high values, disproportionately high values, so you didn't see anything. So when I switch that off, you can see the square matrix compare a lot. You can see the scores a lot better. Okay, so I didn't do anything, just switch the diagonal off. So far so good? Yep. Next, I'm supposed to do a trio, and I just found that I made a mistake here. So you need a upper triangular matrix and a lower triangular matrix. So TRIU and TRIL, lower triangular. So I just made a mistake here. This should be the lower one. Okay. Oh, is it correct? So if I do a lower triangular matrix, I just get any things below, yeah? Then if I do an upper triangular matrix, I get the elements, the matrix at the top. Okay? But I'm trying to take the average of the two. So maybe I need to flip that one of them the other way around. So I actually discovered I just made a mistake here. So this is supposed to be a lower triangular matrix, but that has been flipped upwards. So I put the single quote. So I actually transpose the matrix. Yeah.
Is that how you
Yeah, that's how you do the transpose. This is the original matrix, and then a prime will transpose the matrix. So you see 58 was on the left, now it's on the lower left, now it's the upper right. So the whole matrix is transposed. Because I want to take the average and now focusing on the upper bit. And then multiply by half. So I take the average. No? This is the way I take the average, but using only the upper matrix. Okay, now I'm going to show the matrix that has been symmetrized, but retaining only elements in the upper corner. Yeah, I could have reflected it down to the lower corner. Doesn't matter. But I've just, this is the average of the two matrices, but taking into account the upper parts only. Yep, so far so good. So what I'm going to do now, if the row are the templates, the column be the query samples. So the template on the left would be like each user. In fact, doesn't matter. Here we have 3 fingers, but each of them have 5 samples, right? So that means 15 samples on the column, 15 samples on a row. The program doesn't have to know that this is a template of the same fingers or not. But this is when we start to say that these are positive scores, these are negative scores, that we have to sort things out. And then say that these are genuine scores, these are imposter scores. So genuine scores are scored as a result of matching from the same samples. If it's imposter scores, these are a pair of samples. The scores came from matching as a result of 2 different samples from 2 different people. Is that alright? Okay. Next, we're going to create a mask of the genuine scores. Okay. So first, I'm going to create an identity list. It usually helps a lot so you can type it by hand if you want. It's just a fancier way creating 1 5 times, 2 5 times, and 3 5 times. Okay. So now I got an index saying this is user 1, this is user 2, this is user 3, and the row and the column is exactly the same one. Okay. Now I'm going to create a mask and say, okay, I'm going to run the whole thing and show you the results. The piece of codes are quite fancy, but what it does is really simple. It's trying to say that, okay, there are actually 3 users, and these are their genuine scores. This is a score as a result of finger 1, that's a result of finger 2, because that's 1, 2, 3, 4, 5. So impression 1 compared with impression 2. Impression 1 compared impression 3, 1 compared impression 4, and finger 1 compared impression 1 compared with impression 5, all the same user. And then you do the exhaustive pairwise 2 to 3, 2 4 to 5, 3 4 3 5. So these are genuine scores, right, of the same users. And then I repeat the process for the other fingers and the other fingers. Now all these 3 yellow parts become my genuine scores. How about the imposters one? Yeah. So the next line of the fractional codes, prepare the mask and then show the mask of the imposter score, which is this. Anything that outside the area, this is an imposter score, right? So the genuine score will be somewhere here, here, and then there. The imposter will be the yellow one. So I have the mask that's ready for genuine imposter. I call it mask genuine and mask imposter. Okay? So I programmatically define where the scores are, where the mask is. All I need to do now is now I can visualize how it looks like for the genuine scores and how it looks like for the imposter scores. Okay? Now I can also show the scale using color bar. Then you can see exactly what these values are. It's between 0 to 20. Okay? But that's just for the sake of understanding. In fact, I'm purposely using a small toy data so you can understand how to run a biometric experiments. In real life, you're going to do huge number of experiments. If you have 100 samples, you're going to do 100 by 100. If you have 1,000 samples, you're going to do 1,000 by 1,000. And it's going to be very huge matrix. So you're not going to be able to do it by hand. This is why I programmatically create the mask. Okay? So now I'm going to get the scores out of the mask, and the way is all the mask that has 1 for the imposter and then but only those scores that I'm interested in. You know, I have the score of the symmetrized score. Yeah, this is a symmetrized score. It's a square matrix, the one you see in upper matrix. And I got the mass already. I just multiply the score and the mass. And in fact, I'm going to find the indexes and then put them in a column vector. So here's a command to do that. This is a matrix, and these are the indexes. Okay, this one give me the indexes. It give me the indexes of the imposter score. So then, what this does is it's going to give the scores, the imposter scores that I want. And now in a single column vector. So now you only have one column. See that? So we do the same for the genuine score. So you can see the imposter scores here. Genuine score has got 30 of them, and the imposter scores are here. Okay. So we have a lot more imposter score than genuine score. This is normal. Your positive class has many times fewer samples than the negative samples. Okay. Now I'm going to add the library, which plots the error rate. So I created a function for you. All right. Let's see where I have it. Just wondering whether I have not put it there. Oh, right. I forgot to put the functions in the library. In the GitLab, yeah? One of the GitLab files, yeah? So, okay, I forgot to put it there. You download it from here?
You can download from here. I think it should be in EGFR classification.
Oh, EGFR classification. Alright, okay. So I have it somewhere. This one is used in my research group, yeah? We use it extensively for our project. So this file here, so the global library. This is the one, yeah? So, alright, thank you. So I'm gonna paste the file there, and I'm gonna update the library, the repository. Right. I didn't realize that I didn't put the library there. Right. Okay. Alright, it's there. Oh, there's a library file, isn't it? Here, there's one. Oh, there are many stuff there. Right, okay.
The whole library.
The whole library, alright, okay. So all you need, you don't need this bit. You need that bit. Alright, okay. Alright, okay. There are quite a lot of stuff that going on there. Oh, wrong place. Library, and I'm gonna remove this bit, yeah? They are not well documented, so right, okay. So we're gonna add the library. So I just added another set of functions, but all you need to do really is one function call, okay? So there, like include library, we also have the same thing here. So we're gonna include that WER function, which does the performance add path to the program, yeah? So So library that, alright, this is the one. So that's a path I need. So because I'm in Windows, you know, the path is on the slash. Okay, it's okay. It's the same direction. That direction. It's no problem. Okay. So I'm going to add path to the library, and that path contains only one function that I need. Okay. I wouldn't care about explaining the whole thing, but I'll come in a minute. So where is the file? Okay, the figure is up here. So the genuine score are expected to be higher. We have about 75 of them. And the imposter score, we have numbers of that here, right? So this is the density of the score distribution. So it looks about right? Similarity scores should be higher, and that should be on the right-hand side, whereas the negative scores, imposter, should be on the left-hand side. These are similarity scores. They should be smaller. Now, for this fingerprint experiment, the scores are never always greater than 0. Okay, and then this is a false acceptance rate versus false rejection rate curve. You learn about that in your class, false acceptance and false rejection. Yeah, in maybe AI class or computation intelligence class. So false acceptance is that this is a false rejection curve. This one. So false rejection is an error where the system say that this is not the person when it is actually the same person. It's a genuine person that's been rejected, so there's a false rejection. So as you increase the threshold, so you put the threshold there, and as you increase the threshold, the false rejection rate curve goes up. Okay, in the end, if you put a threshold at 100, you reject everybody, so the false rejection area is going to 100%. Right, so a system that's operational should be somewhere between here, around here. And this software tells you where the threshold should be based on the pair of scores, positive and negative. The other dash curve is the negative scores, and this is a false acceptance curve. So if you put a threshold, and then think about what happens when you put the threshold and then slightly increasing to the right hand side. Yeah. So and then anyone on the left of the threshold, say there's a threshold, anything on the left of the threshold will be rejected. Anything on the right of the threshold will be accepted, right? It's the same, it's considered the same person. Anything on the left will be not the same person. So we are trying to optimize the decision threshold here. So when you are, so if you increase the threshold on the left, your false acceptance rate goes down naturally. Yeah, because false acceptance rate is when we say, when the system will say that the false acceptance rate is the system is making a mistake saying that this is the same person, whereas actually the samples are from different person. Okay, understand? So then that's why if you increase the threshold, the false acceptance rate will go down. But there's a trade-off between the two, and this is the sweet spot. Yeah. Okay. So the operational threshold that you should use to accept or reject a person is given by this function on the data set that you have. So the output of this, if you look at the WER, you see that the threshold is the second parameter. The threshold that minimizes the error. Okay. So and then you can, once you get the threshold, you can use it in your Android phone if that's what you're developing here, or on your computer. Okay. So and the value would be, so I'm going to create an output called thresholds. It will tell me what's the optimal threshold to use. Again, I use Control Enter to run in Matlab, and now I check the threshold. It's 13. So 13 will be optimal threshold to use. It's a sweet spot that adjusts the error between false accept and false reject. Okay. Finally, you want to plot the curve FAR versus FRR, and this is the curves how it looks like. Okay. And here is the weighted error. It's just the average of the two curves. Yeah, the two curves average multiply by half of each, and then sum it up, you get these curves. Again, it shows that minimum error is somewhere here, close to maybe 15, 16. Okay. So there you go. You have a complete experiment. And in this very short tutorial, I showed you how to run a biometric, design a biometric experiment, run it, and then get the scores out of the systems, and then evaluate their performance. and also show you how to use Matlab to do things. Okay, very brief tutorial, and if you ever get lost, I'm going to upload this on the YouTube, and you can